Today, we will use a scientific perspective to explore the complex truth behind meteorological events. According to the latest news from the BBC website, on December 3rd, the Merapi volcano at an altitude of nearly 2,900 meters on the Indonesian island of Sumatra erupted. The volcanic ash shot straight into the altitude of more than 3,000 meters, and several kilometers were shrouded in volcanic ash clouds. About 75 climbers they had already set out to climb the mountain and were therefore trapped on the mountain. Currently, most of the climbers have been evacuated and are being treated for burns. The authorities confirmed that 11 climbers have been confirmed to have died, and search and rescue personnel are searching for at least 22 missing people. So far, 49 people have been successfully evacuated. 8 of the rescued climbers had to be sent to the hospital for treatment due to burns, and 1 suffered a broken limb. After the volcano erupted, 2 local hiking routes were quickly closed, and villagers living on the slopes were advised to stay at least 3 kilometers away from the crater. About 1,400 people live in the hillside village. Some villages were covered in falling ash and the sun was blocked by volcanic clouds. At present, volcanic ash rain has reached Bukit Tinggi, the 3rd largest city in West Sumatra, and residents are called on to wear hats, glasses, and masks to protect themselves from volcanic ash. Search and rescue officials in Padang, the capital of West Sumatra province, said about 168 rescuers, including police and soldiers, had been deployed to try to rescue all trapped climbers and residents. Merapi's alert level currently remains at level 3, with the highest level being level 4, and authorities have been closely monitoring the situation after increasing volcanic activity was detected in recent weeks. Merapi volcano is one of more than 120 active volcanoes in Indonesia. It has been showing signs of activity since the beginning of this year. Indonesia itself is located in the Pacific Ring of Fire, and earthquakes and volcanic movements are quite active. The formation principle of volcanic eruptions is relatively complex. First of all, there are convection movements within the crust, and there are subplates between oceanic plates and continental plates. These plates collide, squeeze, or sink with each other, making the crust in some areas extremely thin. These weak areas make it easier for high-temperature magma in the mantle to rise into the crust, forming volcanic belts. For example, the Pacific Ring of Fire is located at the junction of multiple plates, with frequent magma activity and densely distributed volcanoes. Secondly, after the mantle magma is heated and moves to the high-pressure area under the Earth's crust, it will rise along cracks or faults in the formation. These channels are called volcanic feeding pipes. Pipes can be temporarily blocked, but will reopen as pressure builds. Fresh magma injected into the old pipe will slowly melt the surrounding rock, causing the pipe to expand day by day. Generally speaking, there is isotropic pressure inside a volcano, which mainly comes from the heat energy supplied to the volcano by mantle convection. This causes the volume of high-temperature magma in the volcanic pipe to expand and release volatile gases such as water vapor, carbon dioxide, sulfur dioxide, etc. Pressure sources also include the temporary storage of hot water above when the pipeline is blocked and the vaporization of groundwater, lost through penetration through the pipeline wall. The combined effect of all these pressures will gradually increase the pressure inside the volcano. When the pressure inside the volcano exceeds the stress that the surface rocks can withstand, it will break through and reach a critical state, and the blockage in the volcano pipe and the top will be forced to open. The huge pressure is released, and the rocks and volcanic ash around the crater are ejected into the air. After falling, they spread around, causing the volcano to erupt. Eruptions generally have three stages: intensification, peak, and decay. During the intensification period, the pressure gradually increases, and during the peak period, the pressure is the largest, leading to the most violent eruption. During the decay period, the pressure is released, and the eruption gradually weakens and stops. The power and duration of an eruption are affected by many factors, including the volume of the volcano, the development of capillary channels that supply magma, the distance between the volcano and the upper mantle heat source, and the connection between the pipe and the water reservoir. The mechanisms of different types of volcanic eruptions also vary. For example, gentle shield volcanoes in Central America tend to exude small amounts of highly viscous lava, while less viscous basic magma rich in volatile gases will erupt in steeper stratovolcanoes, forming a violent volcanic explosion. By observing changes in various precursor phenomena such as volcanic earthquakes, ground strain, temperature, and gas composition, we can infer changes in the activity of magma and pipes inside the volcano and provide early warning for possible volcanic eruptions. At the same time, methods such as remote sensing monitoring and numerical simulation of volcanic eruptions are carried out to grasp the status of volcanoes in a timely manner and improve the ability to predict volcanic eruptions. At present, the places most prone to volcanic eruptions in the world are mainly concentrated in the following types of areas. The first is the mid-ocean ridge, where the crustal movement is the most active. The newly generated seafloor expands and magma flows frequently, so there are tens of thousands of submarine volcanoes distributed. They spend most of their time dormant, but small eruptions occur frequently. The mid-ocean ridge volcanic belt surrounds the entire Earth, with a total length of nearly 80,000 kilometers and is the longest volcanic mountain chain. Secondly, there are volcanic arcs located at the edges of subducting plates. As the oceanic plate subducts towards the continental plate, a large amount of seafloor sediments with water content will participate in the generation of magma in the interplate area, which makes the eruption of the volcanic arc more violent, such as the Pacific Rim volcanoes, the Japanese archipelago, Mariana Islands, Andes Mountains, etc. in the belt. Next, there is the hot spot, which is an abnormally high temperature area in the shallower upper mantle, making it easier for magma to generate and rise to the surface. Therefore, volcanoes are densely distributed and active, such as the Hawaiian volcanoes. At the same time, transformation faults are large faults connecting both sides of the mid-ocean ridge axis, with frequent magmatic activity and common volcanic distribution, such as the Kolbek Absolute Fault offshore Iceland. In addition, generalized volcanoes are centers of surface magma activity stimulated by mantle hot plumes. They are mainly found in ancient stable areas. Because the rising magma failed to erupt directly, it replaced surrounding rocks along the way to produce various mineral deposits, such as Nyquist in northern Canada, supervolcanoes and their underlying silver and nickel deposits, etc. In general, these pipes for rising magma are well developed, and the weak areas of the Earth's crust gather most of the volcanoes on the Earth, where volcanic eruptions are most concentrated. Monitoring changes in volcanic activity in these areas is of great significance for preventing volcanic disasters. In fact, when observing and judging a volcano, we must first determine whether it is an active volcano or an extinct volcano. Volcanoes with records of volcanic eruptions in historical periods can be considered active volcanoes, while volcanoes that have no record of eruptions and have last erupted more than 100,000 years are usually considered extinct volcanoes. The age of the last eruption can be roughly determined by analyzing the dating of volcanic eruptions. The tops of active volcanoes are steeper and are distributed along volcanic belts, while the peaks of extinct volcanoes have become flatter due to long-term erosion, and the mountains have become more uplifted, and they do not follow the direction of modern volcanic belts. Active volcanic mountains are also larger in size, and their size reflects the activity of the volcano. The main crater of the active volcano is clearly visible. However, the edge of the extinct volcano crater is irregular, with more collapse and accumulation on both sides, and the main volcano crater may also be cut by smaller subsidiary craters in the later period. Affected by the rising heat movement inside the volcano, the ground temperature in active volcano areas is relatively high, and obvious hot spots are common. The ground temperature of the extinct volcano is basically consistent with the surrounding terrain. Active volcanoes are often located in active areas of crustal movement such as plate boundaries. The distribution of extinct volcanoes is no longer limited to present-day tectonic settings. Active volcanic areas are more likely to induce secondary disasters such as mudslides due to frequent volcanic eruptions. There are fewer such phenomena in extinct volcanoes. Comprehensive analysis of these characteristic elements can more accurately determine whether a volcano is in an active period or is extinct. We must focus on strengthening monitoring of active volcanoes to prevent volcanic disasters. At the same time, before a volcano erupts, there are usually some signs that can be judged and warned in advance. First of all, as the magma and gas inside the volcano rise, various types of volcanic earthquakes will be triggered. Common ones include long-period earthquakes, volcanic microcontinuous shaking, volcanic low-frequency earthquakes, etc. Changes in the magnitude, intensity, and frequency of these earthquakes can determine whether magma is approaching the surface. Secondly, various deformation features will appear, including the volcanic body itself or the nearby surface, such as volcanic expansion, slope increase, new cracks, ground rising or sinking, etc. Using satellite image comparison, inclinometers, strain gauges, and other equipment to assist monitoring, small changes can be compared. In addition, the increase in the temperature inside the volcano will lead to an increase in the emission of heat transfer gases such as carbon dioxide, helium, and radon. Carbon monoxide indicates that fresh magma is close to the surface. Basin-type large volcanoes also have burned vegetation. Gas detection is of great significance in judging changes in the internal state of volcanoes. What cannot be ignored is that the interaction between groundwater and rising hot magma and gas will change spring water temperature, pH value, chemical composition, discharge, and other parameters. Some newly created hot springs can also serve as signals of volcanic anomalies. The most important thing is that changes in magma water content and melt convection in the pipe will affect the distribution of the magnetic field in the volcanic area. Repeated measurements and analysis of abnormal changes in vertical magnetic intensity on volcanoes are very helpful in detecting underground magma activity. Others, such as changes in the migration directions of animals and plants and abnormally strong atmospheric electric fields, can also be used as reference signs. Comprehensive analysis and monitoring of changes in various abnormal omen signals can predict the possible eruption time and scale of the volcano, prepare for disasters, and minimize the loss of life and property. When encountering a volcanic eruption, in order to maximize the chances of escape and self-rescue, nearby and surrounding people should take countermeasures according to different locations and situations. First of all, it is necessary to understand the volcanic mechanism, historical activities, and escape routes in advance. Pay attention to volcanic activity warnings issued by relevant departments and be prepared to avoid danger in advance. Secondly, immediately after the eruption, wear masks, goggles, and other protective equipment to avoid inhaling volcanic ash. Large amounts of volcanic ash can cause respiratory, eye, and other diseases. Evacuate as quickly as possible outside key monitoring and early warning areas. Determine the wind direction, avoid downwind craters, and look for leeward slopes of mountains that can provide shelter. Watch out for volcanic bombs under your feet when moving. In addition, when driving to evacuate, you must plan your route in advance, avoid steep slopes that may collapse, and pay attention to the real-time conditions of the road. Windshields are cleaned frequently and distance is maintained in the workshop. Plan multiple alternative routes. When evacuating, bring basic daily necessities, first aid medicines, radios, etc. Pay attention to keeping yourself warm to avoid typhoid fever and physical exhaustion. Travelers should look after each other to avoid getting lost. When it cannot be ignored, special attention should be paid to the possibility of debris flow disasters in river valleys. Pay attention to mountain collapse warnings to avoid being trapped. Ships should quickly sail away from offshore volcanoes and avoid volcanic islands. Pay attention to tsunami warnings and be prepared for the possibility of tsunamis triggered by volcanoes. More importantly, to avoid danger indoors, choose a room with reliable structure and sealed window gaps. Reinforce doors and windows to prevent volcanic bombs and smoke from entering. Cut off ventilation and air conditioning and seal sewer holes. If there are no evacuation ships, residents of volcanic islands should abandon coastal lowlands and quickly evacuate to the highlands of the island for safety. After a volcanic eruption, it is still necessary to guard against the possibility of secondary disasters, such as mudslides, landslides, or landslides caused by earthquakes. After a volcanic eruption, we must be very careful about the occurrence of various secondary disasters. First of all, a large amount of pyroclastic material produced by volcanic eruptions accumulates under the action of precipitation and moves downward rapidly, causing high-speed and long-distance debris flows with great power. Steep slopes exceeding 50 degrees are more likely to cause debris flow disasters. Secondly, the high-temperature and high-speed fluid composed of volcanic gas, dust, and various debris produced when non-mixed volcanic eruption clouds fall rapidly under the action of gravity is called pyroclastic flow. Its temperature can reach 700 degrees Celsius and its speed exceeds 100 meters per second. It is so powerful that it can refill canyons and is more destructive than mudslides. At the same time, volcanic eruptions can cause strong vibrations in the mountains, and rainfall erosion can also cause slope instability, thus triggering large-scale mountain landslides or debris flows. The frequency and scale of such disasters are mainly determined by topographic conditions. Gas pollution such as carbon monoxide and sulfur dioxide emitted by volcanoes can endanger lives. Sulfur dioxide that diffuses into waters through the air can also cause acid rain, seriously affecting the ecological environment. More importantly, volcanic earthquakes can collapse buildings and trigger tsunamis, jeopardizing the safety of neighboring countries. What cannot be ignored is that the large amount of fresh volcanic material accumulated on the volcanic crater and volcanic Peaks overweight and compacts the lower layer, coupled with the penetration of precipitation, it is easy for it to suddenly collapse and cause a landslide. In addition, the heat generated after an alpine volcano erupts can accelerate the melting of remaining snow and combine with precipitation to form a flood peak, causing floods in the crater and surrounding areas, such as the ice and snow disaster in the Loja volcano in the Nueva Mountains of Colombia in 1985. Thank you for liking, leaving a message, subscribing and turning on the little bell. We will update the latest news from around the world every day. Continue to use a scientific perspective to explore the complex truth behind meteorological events.